right, we're going to take a look at a hypothesis test for a difference of proportions. When we're working with two proportions, our null hypothesis is always that the two proportions are equal. But we could also write this hypothesis as P1 minus P2 equals 0. And so this is why we refer to it as a difference of proportions. Continuing with the idea of using a theoretical distribution, we have now a standard error formula. This one is a standard error for a hypothesis test. It is slightly different from the standard error for a confidence interval. Here we have, notice, just a single p hat that's repeated in all of these. That's not a p1 hat and a p2 hat. We're not talking about the individual proportions from the two samples. What we're actually talking about is what we call the pooled proportion, which is if we take the total successes, where by successes I mean whatever it is we're counting, and we take all the successes from both samples and pool them together, and I also add my two sample sizes together so that that's also the pooled sample size. This is what we call the pooled proportion, and under the null hypothesis, the two proportions are equal, and that's why under the null hypothesis it makes sense to go ahead and just combine the two data sets to make one big one. Now, a few important things to note about this formula. One is that we have links in Blackboard you can use. So on homework you're going to use a Visualize Applet that we have a link to in Blackboard. We'll see where that is when we get into our first example. Also on tests you won't have access to that applet, but you will just be given a standard error calculation. So you will not be expected to use this formula at all. You are not responsible for this formula. We're providing it just because it does offer a little bit of insight into the calculations, especially if you're a little bit mathematically inclined and you find some comfort in the formulas to start with. So based on this standard error, we now have a z-statistic which follows the same form we've been following for all of our z-statistics. Sample statistic minus null parameter. Our sample statistic, if we're working with a difference of two proportions, is always going to be p1 hat minus p2 hat. And the null parameter is what p1 minus p2 is equal to under the null hypothesis, which as we can see up here is equal to 0. And then that standard error really comes from this formula we just talked about, or it comes from that standard error calculator that we have a link to in Blackboard. So when we put all of this together, we get a simple formula for our z-score. It's p1 hat minus p2 hat minus 0, which we don't have to write, and then divided by the standard error. So let's put all of this to some use in an example about smoking and pregnancy. We're interested in addressing the question of whether the proportion of successful pregnancies is lower for smoking women than for non-smoking women. And we have a bunch of values here that are counts from a study. So let's state our hypotheses first. Our null hypothesis is that the rate of successful pregnancies, or the proportion of successful pregnancies among smoking women, is the same as the proportion of successful pregnancies among non-smoking women. Our alternative hypothesis is that the proportion among smoking women is lower than the proportion among non-smoking women. And we could write each of these hypotheses as a difference of proportions also. PS minus PN equals 0. PS minus Pn is less than 0. It can be important to write the alternative hypothesis this way so that we can tell whether we have a left tail or a right tail test, provided that we stay consistent in the order of our subtraction when we calculate our sample statistic. So this should be a left tail test, and the way that we're going to make sure it stays a left tail test is by calculating our sample statistic as PS hat minus PN hat, not in the opposite order. So getting to our sample statistic, let's calculate each of these individually. My estimate for the proportion of successful pregnancies among smoking women comes from our data, and that is 38 out of 135, which comes out to be 0.281. Our estimate for the proportion of successful pregnancies among non-smoking women is 206 out of 543, which comes out to be 0.379. And now, staying consistent in my order, my sample statistic is PS hat minus PN hat, which comes out to be negative 0.098. Now I'll mention it would have been fine to subtract in the other order as long as we stay consistent with that in all of our statements, including our hypotheses. Okay, at this point we'll go ahead and calculate standard error using the link in Blackboard. So let's go ahead and see where we can find that. From Blackboard, there are two places we can find this link. One of them is in the item for section 6.3. We have a link in this description, standard error applet. The other place is if I look over on this menu to the left and scroll down, under external links you'll see this SE calculators. That's standard error calculators. They don't both take you to the exact same page. If I click on SE calculators, you can see that you have links to various different calculators, and I would want to look up the appropriate one, SE for the difference of sample proportions, and click on that. If I go straight from Blackboard in section 6.3, it takes me directly to the standard error calculator that I want. Now I'm going to go ahead and stick with this default of counts as my successes. Again, the successes in this case is successful pregnancies. We call it successes even if it's counting something that doesn't sound like it would be a success, like an incidence of cancer or a worsening of a tumor or something like that. Successes is the word that we use in statistics for whatever it is that we're counting for our proportion. So I'll enter my counts for sample 1. That's 38 out of 135. And for sample 2, that's 206 out of 543. And I do want a standard error for a hypothesis test. The two standard error calculations do differ slightly from one another. So make sure you select the appropriate one. And I have my standard error down here as 0.04616. I'll go ahead and take all decimal places of that because it's just not that hard to work with. Now for my Z statistic, recall we have this nice formula. This is going to be a really easy calculation because I already have both of these quantities calculated. My PS hat minus PN hat is negative 0.098, and my standard error is 0.04616. So I get a z-score of negative 2.123. We'll go on with this hypothesis test in a moment, but I'm just going to come back to our standard error calculator and point out that if I had selected proportions instead of counts, the interface doesn't look any different, but I need to enter those proportions that I calculated, 0.281 and 0.379, and compute. We can see it comes out to be essentially the same. It differs in the 10,000ths or 100,000ths place just because we had done a little bit of rounding on those two calculations. But if you're given your information as proportions instead of counts, don't think that you have to back calculate the counts in order to use this calculator. Okay, we'll go ahead and complete this hypothesis test now. Now that we know the z-score, we can draw a brief little normal curve down here. Since we're talking about a difference of proportions and the null hypothesis is that that difference of proportions is 0, our distribution would be centered at that null value of 0. And we want to be just a little over 2 standard deviations away on the left. So this is where I'm going to mark my sample statistic of PS hat minus PN hat equals negative 0.098. Just barely fit that in there. And what I want is the area in the left tail, because we decided this was a left tail test. Now we can use a table for an estimate of the p-value, and we can use StatKey for a more precise value. So let's start with table A. There's 2 places that we can look up table A. One is the version of it that's printed into our 6.1 notes for one proportion, and the other place we could go is in Blackboard, pulling up the whole table. So coming to Blackboard, let's just pull up the whole table this time. If I scroll down a bit under Datasets and Handouts on the menu to the left, I can go down to where it says Handouts. And here in Handouts we have Table A. Here is our normal table. And we have a z-score that is between 1.96 and 2.326. We want a one-tail area, so our p-value is between 0.01 and 0.025. So it's between 0.01 and 0.025. We can tell from this that we would reject at the 0.05 level, and we would fail to reject at the 0.01 level. And what this gives us is fairly strong, but not very strong, not overwhelming evidence against the null hypothesis. Let's take a quick look in StatKey at what the more precise estimate of this p-value would be. In StatKey, we will go to Theoretical Distributions Normal, left tail, and overwrite this boundary value here with negative 2.123. So it looks like we have a p-value of 0.017 based on this. And we can see that that gets us absolutely consistent information with what we found from Table A, just a little bit more precise. So our conclusion is that we have strong evidence that the alternative hypothesis is true. I just need to word that in a way that is non-technical and is in the context of the original question. So in our conclusion, we state we have strong evidence that the proportion of successful pregnancies is lower among smoking women than among non-smoking women. Note in this conclusion that we can generalize to the population. Assuming we have a random sample, let's back up and look at that. From a study of 678 women attempting pregnancy, well, let's say, assuming that this is a random sample or an approximately random sample of the population of all women attempting pregnancy, we can generalize to the population. We cannot conclude that smoking influences fertility from this. This is an observational study. Smoking most certainly was not randomly assigned. That would have pretty serious ethical problems to try to do a study like that, especially among women who are trying to get pregnant. So we can't conclude that the smoking impacts the fertility. There are all sorts of confounding variables that could be present. It could be that people who smoke tend to also engage in other behaviors as well, and maybe those other behaviors are influencing the chance of getting pregnant, right? So we don't really know for a fact that it's because of the smoking. But we can make this statement here, which is just describing an association between the two.